Okay, I hope that you have the chance to work a little bit with the exercise. Shall we see the solution to this one? Let me see if I can share. Need to stop and share window. Can you see is the text big enough? Okay. So yeah, let's solve it together. Actually, I didn't have, let's say, the time to test it. So let's do it together and see if that works. So the exercise is to we have a vector, an array. We need to copy the array from the memory host to the memory host doesn't sound from the host memory to the device memory, and then we need to do the other way around to copy from the device memory to host memory. We are using for the copy. We are using two arrays on the host. We are using the input array, that this is h underscore x, and h underscore out is the array that we get from the device. So the exercise has 4 parts. The first one is declare and allocate the memory, the device memory dx. A moment. So let's do that. We need to define the variable. Let me see if I can, yeah. So will be double, and it will be dx. And we initialize to null. Also, I can add here a comment if I want. Right. So this is the part 1. Let me check. Declare and allocate. Okay. So I need to. This is already declared. So I need to scroll and is allocate the memory on device. To allocate, I need to use. We use well, we could use malloc, but because this is in the device, we use heap malloc. If we were in programming for an NVIDIA GPU, we will use CUDA malloc. But here in this case, it's a heap malloc. I will semicolon. And now I need to remember the parameters that I need to use. First one will be the pointer. So the pointer is d underscore x. And I need to remember that to send this by reference, because dx will be modified. So I need to send the address. So I will use ampersand. And then I need to specify what I want to allocate. So what I want to allocate is already defined here. If we scroll back, scroll up, we see that we have here s set, that this is the array length multiplied by the size of a double, that we get this with this function. So this is what I want to use here. And you may remember that every time that we execute operation on GPUs with the heap library, we should use heap assert. Oops. So yeah, this should be the first part of the exercise. Let's scroll up. Second part is copy host array hx to device array dx. Okay, so let's go to the copy. Well, actually, yeah, the part is here. So to do copy, because this is already done, I will delete that. Copy input array from host to GPU. So what I need to do here is heap mem copy. To remember the order, the trick that I normally do, what I want to do is to copy the input array from host to GPU. So I want to perform this operation, right? I will comment this. So because I want to perform this operation, the first two parameters will be d underscore x. The second one will be h underscore x. Also, I need to specify the size that I want to copy. That will be SZ. I need to specify the direction that if I want to copy from host to device, from device to host, etc. For that, I will need to use the constant of this is already defined on the library heap mem cpy host to device. This is written in I think it's called camel case. So yeah, the first letter of the word is in capital minus heap. So this will be the operation. Again, I need to use heap underscore assert. Oops. So yeah, there is a question in the chat. So heap assert, what I'm doing here is behind the scenes, I'm calling my error handler. So you see that we define heap assert is it's a definition. I forgot now it's a definition that behind the scenes call my error handler. If we scroll down, we see that we read the heap error. So in the chat I see that this error equal heap malloc. So what I'm doing is I'm reading the return of the function and I processing the error with this function. It's a macro is what I want to do. Yeah. Not sure if that answers your question. So in case that what is returned by the function is different to heap success, print the error and finish the execution of the code. So what we provide is when this is not sure if that when the okay, when we call, for instance, a heap malloc, heap CPI, CPY, etc., we call it this function, let's say heap CPI, returns a value that could be if it's a heap success, the function works okay, so we don't need to do anything else. But it could be that for some reason it doesn't work. So rather than returning a heap success, returns another value. So what we do is we call heap assert, and this macro is a macro that calls a function that reads the return code and prints the error that is associated with that return code. We use this macro to make the code more readable. Otherwise, every time that we execute a heap operation, we would need something like that. Let me. So we will need something like that. Well, this would be cout or cr, but yeah, we will need to process and we'll make the code quite long. So just executing, let's see if I can. That will make a, not sure if that's clear, but yeah, the definition is on at the bottom of the function definition. Okay, so we are here. We made the copy from host to device, and now I need to do the other way around. I need to do the copy from device to host. In theory here, when we will see now later that normally what we do is we copy the information from host to device. We work with that information, and then we copy back from device to host. And then we check the results. Here in this example, what I'm doing is I'm doing only the copy from host to device, device to host, and that's it. Now I need to do heap mem copy. So it will be I'm copying, I'm doing this. I want to do this. So I need to keep the same order. The size that I want to copy, the number of bytes that I want to copy, and the direction that will be heap mem cpy device to host. And yeah, I'm forgetting I need to do again the heap underscore assert. Okay, what else do we need to do? We need to free the device buffer. In C++, we use delete, or if we were using C, we will use free. But here we will need to use heap free. And specify the pointer that I want to free. So now I do here heap assert, and this should be the exercise. Let me check the beginning. So we have done part 1, that is declare and allocate device memory dx, copy the host array to the device array, copy back the device array to the host array x out, and then remember to release device resources dx at the end. Let's see if that works. So I will save. I'm using V, but I think Sonano is available, or if you use Mova extern, you can double click on the file and open it with the browser that you have, no browser, the text editor that you have on your laptop. Save. And now what I will do is I will execute to make. So make is run there. I do ls, and I see that a point out is available there. So what I will do is I will submit the exercise to the queue. So it's sfetch submit.sh. I can check if this is being executed. So with sq ---- me, and it seems that has been executed. I do ls, and the last one seems to be this one here. So if I do cat, let's see if that. So okay, seems that it worked. The number of elements was 256, and correct 256. I will check, for instance, the previous run that was without modification. Cat. So yeah, here I get the number of elements is 256, and the number of correct ones is 1. Do you have any questions? Okay, there are 2 questions. In the first one is about in C++, is it possible to use the standard vector with a non-default allocator to make the memory allocation and deallocation? I imagine this is but you are talking like to I guess that this is for the host memory. The question, I think it's possible. To be honest, I'm more familiar. I'm familiar with the C++, but with like older, like let's say not newer versions of the standard. So I'm more familiar with C, but I suppose that this must be possible. Anyway, I will double check and let you know. There is another question that says, can you show the heap free syntax? Yes, of course. So we have here the file. So for heap free, what I need to specify is the pointer that I want to free. So I specify dx. Remember that dx contains the memory address of the array that we have allocated here. What you may wonder is for heap malloc, we sent the let's see, the dx, we send it by reference here. So I need to put the ampersand because this will be modified. But here, when I call heap free, dx is not modified. What is modified is that the memory that has been allocated is marked as non-allocated, so could be reused if in case that we do another heap malloc. Not sure if that answers your question about heap free. This is the syntax that we have used. Perfect. So yeah, thank you for the questions. That's yeah, good to answer them. Yeah, it's a bit could be a bit tricky to remember the. Yeah, this is sent only by we only send here the value, but when we do heap malloc, because we are modifying this variable, we will need to send this by reference. That is yeah, here. Okay, so let me check where we are. Actually, I can share because okay, I'm not sharing the browser. So the browser will be okay, have a lot of. I think it's this one. So we have covered CUDA heap programming, memory management, and now what we will see is how to execute a kernel, and also will give you time for the to solve the exercises. Is the section 2.2. So we have here the, let's say, the markdown text explaining that we will use some some slides that are available here. So okay, we need to go kernels. I need to share this tab instead. So I guess that as you can see the presentation here. So kernels, we have seen that because remember that if you remember in the morning we have the host that is let's say the CPU with its memory, and also we have the device that is this okay, let's say the generic name is the accelerator, or could be called also a GPU. Is quite used. So the idea is that we send, as I said, we copy the memory, we do operations on that memory, we process that data that has been copied from host to device, and then we copy back from device to host. But the information process that we do, what we call is a function that modifies that data, and normally this function is called a kernel. the GPUs, because of the architecture, that we have a lot of small processing units, it works well when we have a lot of data. So when we have a matrix that contains a lot of numbers, or when we have we can have a picture that we need to process each pixel. So if we have a high resolution picture, we will have a lot of pixels that will need to be processed, etc. And normally this processing is done with for loops. So a kernel, normally what will execute is a for loop on that on the array that is available on the device. We have a simple example here. So here we have a for loop. So we have let's see if that okay, yeah, you can see the. So what I'm doing is this is the array that is in the on the well, let's see, this is the for loop that I want to execute in parallel. And what I'm doing here is that for each position of the array result, I'm multiplying the position by 2. You can see here that this is very important for GPUs, and to gain a good performance, if possible. Could be the cases that we cannot do that because of the nature of the problem that we are solving. You see here that this is all the iterations can be done in parallel. There is no dependency of the previous iteration or the next one. Each element of the array is independent, so can be done in parallel. I think this type of problems are called embarrassingly parallel, because yeah, let's say it's quite trivial to get the parallel solution because there are no dependencies. So what is the way to execute a kernel using CUDA or heap? This is the kernel. So we have here a function. We call it my kernel. We can call it process. We can choose the name that we want. The function doesn't return anything. I mean, return, but let's say we don't care about the return, so we use a void, and we use this qualifier that is called global. For functions, for kernels that are executed on the GPU, we will need to use this qualifier. Later, today, tomorrow, we will see other qualifiers. But remember that for the GPU kernels, we will use global. You see that here in this kernel, we don't have a for loop. What we have here is the same, let's say, the body of the for loop that is here. But I have rather than iterating I from 0 to the array length -1, I will use thread index.x. This is each when we run the kernel in parallel, we will have a block of threads. We will have a lot of threads, and we will have as many threads as elements the array has. So, for instance, if the array length here is 512, I will have 512 threads. So I will perform the operation, the 512 operations at the same time in parallel. Each operation will be done by one thread. And this each processing unit will be unique, will have a unique identifier. So result will be done in parallel. There is a question in the chat that how this, we will see that later. We will see how, because here I'm specifying that it will be, the array will be from 0 to the array length. So here we specify that with the, when we specify, yeah, this will be explained later. Like we need to specify the size of the block and the number of threads that I want to use. The number of threads will be the same as the array length. Let me see if the next, exactly. So we have this function, but yeah, actually, yeah, the question is timely. Is how many threads do I have? How many threads do I need? I need to define that. So I need to define that is now a concept of blocks and threads per block. Block is a set of threads that will execute the operation that. So for we will see later that we can have several blocks, but for simplicity here we will have only one block. Okay. And you see that we have like a 111. What does it mean? It's because blocks is the type of the variable is dimension 3. Because when we here we are executing an array is 1D, but we could work with a matrix. We can work with a 3D array. So in that case, I need to specify the number of blocks in the X direction, Y direction, and Z direction in the 3 directions if we have a 3D. But in this case, because we are using only one block, I specify here 1, 1, 1. Now I need to specify the threads per block. So each block will have a number of threads. Also, the threads could be in the 3D space. We can have like on 1D, like this is what I'm doing here. So we have and let's see, in the X direction, I have array length, and in the Y and Z, I will have only one thread, so I will not have more. So let's say the block will be 1D. And when I call my kernel, that this is the function that I have defined before, I'm sending with this syntax, I send in blocks and threads per block. That this has been defined before. It has been defined here. Now this could be let's say a bit complex, but when we do the exercise, you will understand better how does it work, because we will do some modifications and you will understand that better. But now what you would need to remember is that when we execute when we call the kernel will be executed once per thread. So I will need to be careful with the number of threads that I create. So I will create here, for simplicity, as many threads as I have in my, as elements I have in my array. That is a 1D. Okay, so yeah, what I already said, and yeah, this variable is a struct that is x, y, and z. What happens that we will see later in the what happen if we have a more than one block, because also is yeah, we will see some examples that we shouldn't use like a higher number of threads per block. So the way of getting this index will be to multiply the block ID with the block dimension and the thread ID. Imagine that the block ID, imagine that we have a 2. So will be the block ID index, or the block index will be 0 or 1. So for instance, for the block index 0, this will be 0, and you will access the first block with the thread index. If the block ID is 1, this will be multiplied the block index, well, ID index, multiplied by the block dimension, and then I will use the thread index. As I said, when we do the exercises, you will know it's a little bit, how to say, it's the first time that you see that and could be a bit difficult to grasp, but okay, and here for simplicity, we will see later that it's not always the same. So we have the threads per block. We will let's say, for instance, imagine that the array is 512 and threads per block will be 256. So threads per block will be 256, and the number of blocks will be the array length, that is 512, divided by 256. So we will have 2 blocks. And when I call my kernel, I will specify that we have 2 blocks, and the threads per block, I will specify that we have this number. Normally, we will see later why. Normally, we use a power of 2 numbers of threads per block. So we use 128, 256, 512, 1024. And we need to set the number of blocks enough to solve the problem space. So if we have, if we are using a block size of 512, and we have a problem of 3,000 elements, I will need 6 blocks. So the way of guessing how many blocks do I need is dividing the array length with the threads per block. So we have already seen that we have the grid dimension will be the number of blocks, block dimension will be the number of threads per block, and I define here the block index and the thread index. That these are the block index is unique for each block, and the thread index is unique to each thread. To identify these variables, block index and thread index, will be helpful to identify what element of the array I want to edit. These variables should be considered reserved because we cannot. This is the name that we should use, and we cannot use other names. And Also, we cannot use that name for something else. This is interesting to know that when we call a kernel, this will return immediately. It doesn't mean that the operation that we are performing, that the kernel has finished. But it means that this is an asynchronous operation. So we launch the kernel, and we launch the kernel, and we will need to return to wait until the kernel returns. For that, I will use heap device synchronize. Here in the now I understand the question. In the slides appears like a heap error. We are not using the macro. We are not using here heap assert. This is I guess that this is like maybe to make this more clear. But yeah, now I understand the confusion. But the macro is used for simplicity on the code, because we will execute a lot of heap functions, and it's better to use the macro in order not to repeat code. So before finishing the program, the code that we are running, we will need to run heap device synchronize. That this is a synchronous function. Once that this function finishes, it means that the kernel has been executed. So error handling. So when we call my kernel, you see that here we are not using a heap assert, or we are not checking the error like is checked here. What we do is we execute heap peak at last error that checks if there has been an error when we launch the kernel. But we cannot check if we cannot check. That function doesn't check if the kernel have been executed okay or not. We will see errors when we call heap device synchronize. At that point, we may see if the kernel had an issue or not. So yeah, it's explained there. So the first function, heap peak at the last error, we will see errors when we will see an error if we had an issue launching the kernel. The heap device synchronize, we will not. We will see errors related with the kernel that when this has been run on the. This is another way of launching a kernel. This way is we have seen the previous one, that was this one. But if I want to use a function, I can use this function heap launch kernel ggl. So here I will specify the function, the dimension, the threads, and the size. Yeah, I will specify everything that has been specified before in this when we use the other way of launching a kernel. Normally the fourth and fifth argument are 0, but we can use them. That is explained there that the fourth argument is the amount of additional shared memory to allocate when launching the kernel, and the fifth argument is the stream. We will see streams, if not probably tomorrow. Yeah, these are like different ways of. I agree that what I normally see is this. I see a comment in the chat that this is the way of. So now we will see an exercise to understand how does it work, how the kernels work. So what we will use is the solution of the previous exercise. Now we will add a kernel, and we will multiply each element of the array by a constant that will be, in our case, will be 2.0. You can use, if you move to the, let me stop sharing. I will share my window. So we are now in section 2.01. So I will need to move back and go to the section 2.02. If you do ls, you will find the template, and you will find the parts. So the first part will be write a kernel of the prototype. I see that there are several questions in the chat. I will address them as soon as possible. Sorry, but I will give you time to solve this exercise, and yeah, later we can see the solution. So the first part will be the write a kernel of that actually I think that is already. No, this is the. So yeah, we can reuse the kernel that is on the documentation that we have seen before. We will, in the main part of the program, declare and initialize the variables of type dim3. So these are here. Well, yeah, the kernel will be here. So yeah, we will need to define these variables there. And the part 3, generalize the kernel to treat any number of blocks and problem sizes that are not a whole number of blocks. So yeah, this has three parts. So let me check the time. So we are, it's 20 past 2. In theory, the afternoon break is 2:30. We will have a 15-minute break, and later we will see some performance considerations. But I will give you time, yeah, to solve this exercise. So yeah, we have now 10 minutes. I will review the questions in the chat and give you an answer. Well, actually, I can start with the last one. Is I feel like blocks and threads per block don't need to be constant, so we will be able to parse them from a command line arguments. Is there any benefit to having them hard coded? I don't see like a benefit. I think it's here for simplicity we have them hard coded, but we can actually for testing we can use the command line arguments and test what is the best block size for our problem or for our also for the GPU that we are using, because if there could be different GPU models that maybe one block size will be better than the other. So now I think this could be defined, can be defined using when we call the program, when we execute the software. There is another question in the chat that for Fortran, if these threads and block indices are 0 or 1 based. Fortran not, but I believe that are, you need to be careful with the, because I believe the indexes are 0, use the C or C++ index. But it's something that I'm not very familiar. But it's important. For instance, there is we are learning today how to use a GPU with the kernels. But in case that, for instance, we use directives, we use OpenMP, we should be careful with the indexing, because as you said, Fortran is a 1 base, but all of these, the syntax that we are seeing here is comes from C++. So could be a bit tricky. Okay, so according to the schedule, we are now in the afternoon break. So please feel free to use this break, this 15-minute break. I will give you more, later after the break, more time to do the exercise. The exercise will be reviewed tomorrow. So you will have the rest of this afternoon to work on the exercise. So in case that you don't have the time to finish it, don't worry about that. And see you at 2:45. Okay, so I will give you more time for the exercise, and then we can continue with the rest of the. We have another lesson called performance that has another exercise, and I give you time for there to do the exercises, and tomorrow we can see the solution. So okay, I give you 15 minutes more, and at 3 p.m. we will see the next lesson. Okay, I see there is a question in the chat to find if the thread has access to consecutive memory locations. Okay, this is like a 203. Okay, this is 203. Yeah, this is the performance consideration. We will see that when we don't have like the right access or like a coalescence access, we will have like a longer running time. But this is normally when we run with the profiler, we can check that. What do you want to do? Do you want to see because I was thinking, yeah, we can either see the solution of the kernel exercise either now or tomorrow. Maybe now is better, so you can make progress with the, yeah. So yeah, let's see the solution now, and you can make progress with the manage, sorry, with the performance exercise. Okay, so is everyone else okay? Shall we see the solution to this exercise? Or do you need more time to solve it? Okay, so yeah, let's see. Give me a second. Okay, so here we have we need to implement the simple operation x equal ax for a vector x of type double and a constant a. So we will write the kernel and yeah, go on. So yeah, let's do that. So kernel, we can define the kernel here, for instance. So the kernel, remember that we will use the global, that this is a double underscore void, and what name I can use? Oh well, they said here actually, yeah, it's here, so we can copy that. So yeah, will be called my kernel. So the inputs will be double A and a double X. So this will be the vector of the. Okay, I will delete this. So for the kernel, as I said, we will find, let's say that we want to do it in sequential. So this will be like a for int e equal 0, e less than array length what we'll do is we will do x will be equal to a multiplied by x, something like that. But I need to do this in parallel. So each my kernel, this function will be called once per thread. So I'm getting rid of that, and what I need to make this. So what I'm doing here is I'm I need to define the. Sorry, I forgot to add this. So here I need to define the index. The index will be int I, e, equal thread idx thread index dot x. I have three dimensions, x, y, and z, but because this is a one-day array, I can avoid y and z. So I mean avoid. I don't need to consider these these other dimensions. So this will be, if I'm correct, this will be my kernel. What I'm doing is I'm multiplying A by the position of X, and this will be done in parallel. I will delete this to make this easier to read. So this is the kernel already defined. Let's see if that works, maybe not, but yeah, let's go step by step. We have done the part one, that is write a kernel with this prototype. Now in the main part of the program, declare and initialize variables of type dim3 to hold the number of blocks and the number of threads per block. Use one block and threads per block in the first instance. Okay, fine. So here I have the array length is 256, number of blocks is 1, and the threads per block is the same, 256. So if I need to specify here dim3 the blocks that will be with the curly braces. I can say there 1, 1, 1, but I will use this. I can also use this number of blocks. I will copy and I can paste here, number of blocks. But it's the same as using 1, 1, 1. But yeah, later we will do some modifications and check that. Okay, so now we have blocks, and now I need to define the threads per block. So it's a dim3 threads per block equal so here for simplicity I will use this variable that is here, threads per block 256. One. So we have this defined, and now what I need to do is I need to call the kernel. To call the kernel is my kernel. I will use the syntax, and I need to specify here blocks and threads per block. And I need to also to specify the constant. Constant is, let me check if it's defined, is A and dx. That's it. Well, I'm forgetting something here. That because I'm executing the kernel, but remember that we have seen that the main kernel, this when we call the kernel, this will return immediately and it doesn't mean that the kernel has been executed. So here I will need to add to wait for the until the kernel finish. So I will use heap device synchronize, and I will use heap push ARCHER2. And also I will check if there was an error with the kernel launch. So I will use heap assert underscore assert and heap peek at the last error. So in theory, this should work. Check yeah, seems that everything is done okay. I will save, and actually now I will. Well, I can use. There are two choices. I can. Well, I will copy the make file. So cd section 2.01 make file. I can either do this or let's see if that works. I don't think that will work. Well, I see that I get an error there in my code. So I will reopen the. I see there is a question in the chat that yeah, this heap main copy is blocking, but when I call my kernel, this is not blocking. So I will start copying memory from device to host, and maybe the kernel is still running. So this copy will not be valid. That's why I need to do the synchronization before copying the memory from device to host, because the kernel could be still running while I perform the heap memory copy. Not sure if that makes sense. So the error that, well, I will let me know in the chat if that makes sense or not. I forgot here to put to close the, yeah, to put the brace of the bracket. Let's see if now it compiles. Okay, the way of compiling, because there is no make file here, it will fail and will say no make file found. So make -f, here I can specify the make file that I want to use. So I will use the make file that is here. So specify that. Well, I generated this. You see that we have now the exe file here. So what I will do is I will submit the code. So with the sbatch submit.sh. I will see cq -me. Is it running? Let me check. Yeah, it's run. So let's learn. And yeah, it seems to work. we have a number of elements 256 and correct 256. There is a second option in the, I'm not sure if there are any questions that you may want to ask. If not, I'll continue with the. We can play with the on the exercise. That is, we can use a longer array length and see how does it work for the number of blocks. So yeah, I see that a question in the chat. On the repository, you will find the solution to all of these exercises, and the slides are here. Are on a repository. Let me find you the. I will copy that on the ARCHER2 website, but this is the repository with the slides. One modification that we can do in the code exercise. So I can modify array length, and I can use here 512. Well, I will keep that. I will keep this threads per block, and we will see what happens. So make an s-patch submit.sh. Oh, it seems that is already done. So if I print this, you will see that we have 512 elements, but the number of correct elements is 256. Why? You see that we have 512 elements and the thread per block is 256. But here we will need to use 2 blocks rather than one. So if I modify this like as we said, hard-coded, we'll see if that works. There is a question in the chat that is the best way to time kernels. This will be we will learn that there is a profiler that is quite simple to use, and that profiler will give you an accurate timing of the kernels. Okay, we have compiled. Let's submit with the s-patch. Yeah, it's running. See if, yeah, done. We have this. Okay, so something is wrong here. Let me see the exercise and see if I managed to. Oh, we have threads per block, number of blocks. Okay. You see where the error is? I modify the array length is 512, and the number of blocks is 2. So if I go here, it is okay because we have a number of blocks will be 211, and the threads per block will be 256.11. The call is okay. The problem here is the kernel. This is the kernel. What needs to be modified in order to take into account the number of locks, because in this version only I take into account the thread index. is the index, the variable I. Is that does it make sense? Here I will need to add what I need to add, the block index.x multiplied by the block dimension.x. So block dimension will be 256. This is not working. Okay, it works now. So block index will be either 0 or 1, and this will be the size of the block, that is 256. That is the threads per block. Now it should work. Let's compile with make. Let's submit and see it's running. Runs, and if I copy, now it's correct. Is the number of elements is 512, and yeah, correct is 512. Okay, last. Let's say this is. Let me. Here, what I'm doing is manually. I'm calculating threads per block, number of blocks. This is everything hard coded. What we can do here is we can calculate this on the here when I calculate the blocks and threads per block, I can do this automatically. So depending on the threads per block, I can calculate the number of blocks. Actually, also depending on the array length, I mean, I can calculate the number of blocks. This must be like a fix, but I can calculate the number of blocks depending on the array length and the threads per block that I want to use. So I can use here, for instance, oops, I need to use the array length divided by threads per block. But if I'm using that, I should be very careful that this is array length is divisible by the threads per block. What happens if the array length is another number, like 1000, rather than I will need to use one block more than the than the number of threads per block. What I will do is I will give you, well, you can play this afternoon with that, and tomorrow we can see how we can write like a, let's say, an elegant solution to handle that. Also, when we run more blocks, we need to be careful that we will have more threads than elements in the array. So what we will need to modify as well in the function here, I will need to say if e is less than array length, execute this. Because it could be the case that I could be larger than the array length. So in that case, you don't do anything. That's it. It's not a problem. Any questions, or is that more or less clear what we have done? Okay, so there is a question that is there a way to do this without the conditional that might result in divergence? The divergence is happens in the case that, let's say, for instance, if we have if we have if this is the case, do something, and if not, do another. So in that case, we will have a divergence and will be not good. But in our case, the divergence is do something or don't do anything. So in that case, it's not. It's okay. It's not, let's say, harmful performance-wise. But yeah, we will see later more about the divergence of the. Any other questions? If not, we will continue with let's see, the last lesson that will be performance, and I'll give you time with to do the exercises. What we will do tomorrow morning at 10, we will review what we have learned today and solve the exercises. And also, please, any questions or anything, we will answer them in that time. I can share with you the plan. So if I share this, I think it's this thing. Let me see if So the plan for tomorrow is the reviews the previous day briefly and the solution of the previous exercise. This will be the first 45 minutes. Then we will have the morning break. We will see the types of memory that we have on the GPUs, or how we will handle the memory, so we can use managed memory. And in the afternoon, we can see shared memory and constant memory. And at the end of the day, we will learn about the streams. And now we will see some performance considerations, and also we will have an exercise on matrix operation. So here is the text, and I need to find the slides that are here, and I will share this tab instead. Okay, performance. I was, yeah, I hope that you see the slides okay. So before we have now a simple GPU program that moves data from host to device, do an operation on that data, and then copy back from device to host. So what are the points that we need to bear in mind regarding performance? This is a subset. There are others, but well, it's good to have them now in mind for future exercises, etc. So here we talk about Anders' law that says that the parallel performance of a program is limited by the fraction of the code that is serial. So what that means regarding GPU contexts, that if let's say the part of the program that we parallelize the GPU, if this is a big chunk, we will get a better parallelization, better performance that if for some reason we have a lot of serial code and we have the parallel part, or the part that could be parallelized, the for loop that we will parallelize is small, let's say. So in that case, we will not gain that much performance using a GPU, or what, or even using a CPU, using threads, or using. This is this law applies for all parallel software that could be the bigger the parallel part is, the more performance that we will get if we use several processing units. We have also another concept that this is interesting, that is regarding occupancy. Actually, this, let's say, took me a while to understand, because normally when we use threaded programming when we use MPI, OpenMP, pthreads on a CPU, on ARCHER2 we have 128 cores per node. If we use Cirrus, that is another supercomputer, we have 244 CPUs, CPUs in our node. And normally we have the same number of threads as the number of available CPUs cores. We can see that maybe the performance is not that good, so maybe we have less. So let's say we are a little bit of thread dependent, or let's say dependent on the number of available cores or CPUs. And GPUs is different on GPUs, because we have a lot of cores. We would need we will need a high degree of thread parallelism. That this is here we have the concept of occupancy. So high occupancy is achieved by codes that have a high degree of thread parallelism. So we will need a lot of parallel threads in order to get performance on a GPU. So we will need more threads than, ideally, we will need more threads than the number of available cores that we have on the GPU. And this number is we are talking about around 10 yeah, 100, yeah, would be like a good 100,000 threads, or like as many threads as possible. If we don't have that number, we should question whether a GPU will be suitable or not for our work. Maybe what we want to do can be done on a CPU. We don't need a GPU to run the code. We have a sample here of a two-dimensional loop that you see that we have the outer loop is will run 512 times, and the inner loop will run 512 times. So if we only parallelize this inner loop, the elements that will be executed in parallel will be, or the number of threads will be 512. So 512 is not good enough. Also, each thread will do the outer loop. The outer loop is will perform 512 operations. So the thread will not be lightweight. It will not be one operation. Will be 512 operations. So the occupancy is not that good. But what if we parallelize both loops? And actually here is I'm working with a matrix, and I'm working with now with in 2 dimensions. I'm working with X, and I'm working with Y. Here makes sense when we were using the dimension 3 variables to use the X component and the Y component of that structure. So let's say that I parallelize both loops. So I have 512 multiplied by 512. I have 262,144 threads. So this is a much better occupancy, much better number of threads than 512. So for GPUs, one of the concepts that you need to bear in mind that you need as many threads as possible in order to gain performance, because the threads will be quite lightweight, will be only like a few operations, and this is handled by the GPU runtime easily. So you need a high number of threads to have a high occupancy. Also, here we will talk about memory usage, and this part is a little bit tricky to understand. So I will explain it, but tomorrow I will go through it again, because it could not be clear to it will not be clear. But yeah, I will explain it now, and we can revisit it tomorrow. And please, if it's not clear or if you have any questions, let me know, because this is important that you understand this part. If by the end of today it's not that clear, fine. You can, if you have the time, have a quick look later today. But if not, tomorrow we will go through this again, and we will review this again. Okay, in the CPU, we are aware about the caching behavior, and we are aware that a thread in a CPU code favors consecutive memory accesses. So when we are in the for instance, this is an example in C. To access the element of an array, we will need to access them in a consecutive way. So the indexing the y and j, first we iterate with the I and then with the j. In that case, we secure consecutive access. The cache behavior, the same thread will get access to the to consecutive locations in memory. But in the GPU is different. In the GPU, what we do is like let's say each thread is not accessing consecutive positions of memory. So the way of executing threads on a GPU is with wave fronts. Let me check if I can find like a picture where you can see better this concept. Actually, this will be useful for us if you have a look at this. I will share the link here. Actually, we'll share this tab instead. So here, this is I find it quite useful, this introduction to the HIMP programming model. This is part of the ROCm documentation, and yeah, this is developed by AMD. Here you will find the hardware difference, CPU versus GPU. You see that here we have, maybe you have seen this in the morning, but we have in the CPU less cores and higher clock speed. And in the GPU, we have way more compute units are called here, computing units or cores, but we have a lower clock speed because here we're not, we don't look for like a powerful cores. We are looking for a big number of cores. And this is the normal, this is a GPU program. We have we initialize, transfer data, execute kernel, and return results. So this is the data flow that we use. This is like the structure that we have for hosted device. What I wanted to explain here is that this is the hierarchy of thread groups. So we have the grid, that the grid has several blocks, and each block we have warps. These warps of wavefronts are explained here. That is a group of threads that are executed at the same time. So it is important that each thread on that warp access don't access like different positions of memory, because this will not be coalescence. The size of a warp, depending on the architecture, could be either 64 threads or 32 threads. Here is also explained what a block is, grid, and well, tomorrow we will see more about the shared memory and the constant memory. But yeah, this is something that we will see tomorrow. And this is what I'm talking when I'm talking about the memory access patterns of uncoalescence access and coalescence. So the threads, if this is the memory and this is the thread number. So if each thread accesses consecutive positions of memory, this will be coalescence. But if, for instance, a thread 1 accesses the position 62 and the thread 62 accesses position 1, this will be a bit of a mess and we will not get the right performance. Yeah, here is explain and what we will see tomorrow afternoon. We will see about the streams. So yeah, here you have like a nice view of the. But let me go back to the slides. So for instance, in this case that we are using, yeah, I see that the link that is already shared is this one. So this is I recommend you to have a quick look at that. It's quite well explained. For instance, in this kernel, we have yeah, we have consecutive access. So each the thread I access position I. So it's fine. It's not. We don't have there are no issues. Consecutive threads with the consecutive index access consecutive memory locations. What is a bit tricky to understand here is that in this case, for instance, when we use if when we parallelize because we have the index, the I and J. So if we have access to different positions of J, this will not be coalescence. So to be coalescence, we will need to use the for loop will be on the first on I rather than on J. We will need to iterate over nx rather than over. I think this is easier to see with an example. Let me check if no. Well, here we have the exercise that you can play later today and tomorrow. We will see the solution. I think I found an example here. Isn't CUDA is a let me see if I can make this video. I would recommend you to read this article to understand better this concept. That this is for CUDA, but will apply for HIP because it's, let's say, what we are learning here is to use kernels, not to how to say, but let's see the concept that we are learning here for CUDA or heap could apply. These concepts are general. So in this article is explained the let me see if I can share this. We have the representation of the matrix in 2D, and but in the on the memory is linear. The when we have the one thing is the representation that is here, that this is in 2 dimension, but the memory you see that the first this row will be here, the second row will be here, the third will be here, and the fourth will be here. So if we get access to the, so if each thread access to one position of the, yeah, I noticed that you don't see the pointer of, how can I show this? Is this a way to, So this is what we need to be careful when we execute to the array. We can have this case that let me see if I have a pointer here. Drawing. Yeah, this must be. So in memory we have this is like a one row, that this row will be here, represented in memory. Memory is linear. We have this other row, that is this one, let's say this one here, that this is represented here. So if we are getting access to this position on the array, we are getting access to, I mean, the thread is getting access to this one. But it could be the case that the thread, the next thread in the warp, is getting access to this element here. And this access here will be the, access here, and this one will be here. So for instance, here we will not have a coalescence on the access. But when we do this with the, if we iterate with the right dimension, we will get a coalescence access. This on the on this. If I share that on the again, you will see it. Application script, I think it's this one. Yeah, this one. So here you see that we have a coalescence to the access, but if we do it okay, we will have a coalescence to the access. And in that case, we need to be careful with the positions of the. So I'm just checking the chat if there are any questions. I'm not sure if is now more clear or is yeah, this part is what I will do is for tomorrow I will try to find a better sample, and also when we solve the exercise we will compare with the let me yeah, tomorrow we will continue with the learning about that. I'm not sure if I'm aware that we are already now to the finish that we finished at 4. What my recommendation is, please have a look at this if you have the time. Have a look at this exercise of section performance. That is section 2.03. There is an exercise here that you can play with the iterating using the column or using the row, and you will see the difference. If there are no more questions, thank you for attending today. And yeah, tomorrow we will continue. To check the performance difference, you will see that the submit, when you submit, you see that here we are calling a rockprof. Rockprof, we will generate a file, and you will see in that file will contain the kernel name and the number of milliseconds that the kernel took. Tomorrow we will see when we solve the exercise that to see the different kernel times of the. Any other questions before we finish this session? If not, let's see you tomorrow at 10, and I will go through this again, and I will find a better example to explain the coalescence, and also if you have any, we will play with the GPU on ARCHER2, and you will check what the performance difference we can have with coalescence versus non-coalescence memory access. Okay, so have a nice rest of the day. Also, if you have any questions, I will send you my mail address is j.herrera@epcc.edu.ac.uk. Feel free to send me a message there, and happy to chat. See you tomorrow at 10. Have a nice rest of the day. Bye. Bye for now.